Welcome everybody to our series on computer programming for mathematics. I am Dr. Lathram, and today we will be talking about data types in Python. When we imagine bits actually being stored in a computer or on the hard drive, we'd probably imagine something that looks like this. We just have this big wide expanse of ones and zeros. Now, when we talk about a computer's word size, so the word size is really going to be the smallest collection of bits that are read at a particular time. You're probably used to hearing about word size and maybe not recognizing it, but when we talk about a 32-bit machine or a 64-bit machine, we're actually talking about how many bits at a time that computer is able to handle. So when it goes out and grabs some data from memory, it's going to bring back either 32 bits or 64 bits. Generally, the more bits that you can handle, the faster your machine can process things, and so generally the faster your computer is. But that's kind of a rough idea of what we're talking about. Now, words are generally broken down into bytes, and so bytes, half of a byte is going to be a nibble, and a fourth of a nibble is going to be a bit. So really we've got 8 bits to the byte, 4 bits to the nibble, and a bit is going to be the smallest piece of information that our computer can actually handle, just being either a 1 or a 0. So when a computer reads a sequence of bits into a variable, then it really doesn't know necessarily how to interpret the bits. And so when we say how the bits are interpreted, that's really saying what type of variable that we are using. Now, one of the strengths of Python is that we don't really necessarily have to worry about memory allocation on its own. All that's taken care of. The Python interpreter handles that, and so that's not something that we need to consciously be aware of. Now, that's not true for other languages like C, where we do have to worry about memory allocation. For us, that's not going to be an issue. Nevertheless, our variables are going to be typed. And so when we're doing various types of arithmetic, or it will matter the type of variable that we are using. And so that's why we're kind of going through this material now, so that we have an understanding of what types of variables are available and kind of how they're used, and the structure of Python, of how Python handles them. And so now let's take a look at the kinds of data types that we have in Python. Now, Python has kind of 2 large categories of data types. They have numerical data types and sequential data types. Under the numerical data types, we have, of course, integers and long integers, our floating point numbers, and complex numbers. Now, the complex numbers are that's a little bit different than what we find in a language like C. It's more reminiscent of Fortran or MATLAB, something like that. Under the sequential data types, we have strings, we have lists, we have tuples, and we have dictionaries. And so now let's go over to idle and take a look about how those things are used and how we determine the type of object at which we are looking. And so as you can see here, we are in idle, and we're using Python 2.7.6 is the version that we're using. And so let's take a look at some of our Python data types now. So the first one that we have to look at is an integer. So everybody's pretty much familiar what an integer is. If I just type something like x is equal to 2, then I introduce the type function. So the type function does exactly what you think that it should. It returns the type of variable or type of object that we're dealing with. And so that's, in this case, just going to be an integer. Now, I said that there was a slight difference between integers and long integers. When our integers get too big, then they become long integers. So it's kind of a natural question. How big is too big? And so you can determine that on your system. You can take a look, and we need to import a module. Now, we'll talk about more about what modules are a little bit later on, and if you just want to kind of type along and get a feel for what we're doing, we're kind of, in importing modules, we're bringing in other functions, we're bringing in other programs. And so what I want to bring in, I want to import the sys module. So the sys module actually being the system module. Now the sys module will tell me how big an integer is allowed to be before it becomes a long integer. And so I can do that with the command sys.maxInt. And so it's going to return me that number. And so, okay, that's a number. That's great. That's awesome. What kind of number is that? What is that number exactly? Well, what that number is, it will be really 2 to the 63rd power minus 1. And if you want to see kind of how you determine that, well, let's talk about taking logarithms. So again, this is a little bit beyond just data types, but we'll go through this more later on. But just to introduce them here, if I import the math module, then that gives me access to the logarithm function. And so I can do math.log of sys.maxInt, and I want to do log base 2 of that thing. Well, log base 2 of that thing gives me 63. So really that's going to be 2 to the 63rd power. If I wanted to confirm that, one way to confirm that is I can do this with a loop, again, introducing something a little bit new, but here we go. If I want to start off with a value of 0 and doing a loop, which again, this is a structure that we will talk about later. If I let I, so for I in the range up to 63, so this really is saying that I is going to go from 0 up to 62. What I'm going to do is I'm going to add together all of the powers of 2 from 0, 2 to the 0, all the way up to 2 to the 62nd power. So whenever I add all of those together, what value do I have for x? Lo and behold, that is my sys.maxInt value. So I know that my sys.maxInt is going to be 2 to the 63rd power minus 1. Now, kind of the interesting thing about that, as soon as I go over that power, so just to check, what type of object is x? It's an integer. Well, let's do x equal to x plus 1. And doing that, now what type of object do we have? Now we've got a long integer. And so really not anything different. All the arithmetic is going to be the same. It's more how Python is going to have the structure of handling the digits that are in the integer. It really won't make any difference to us. We have arbitrarily long arithmetic in Python, which means that basically our integers can get as big as the memory that we've got in the computer. And so maybe not quite that big, but anyway, you get the idea. We don't really have to worry about how many digits we can have in our integers. They'll just become long integers, and we'll be fine with that. Now, the downside is that if our integers become too big, then it may really slow our programs down. Nothing that we will do will be that big a deal, and so the difference between the integers and the long integers really won't matter that much for us. So now let's take a look at our floating point numbers. So once we enter floating point number land, we really begin to see that we are not dealing in the world of mathematics anymore. Now we are dealing in the world of computer science. That computers, still being discrete machines, do not have arbitrary precision that we find in the real numbers. That's going to be severely limited. And so not every possible real number is going to find a representation in our computers. And so that kind of, for lack of a better term, quantization that we find in the machine will be important when we're talking about our floating point computations. And so it's something to be aware of as we go about things. So let's come over to idle, and let's say that we start out with a floating point integer. A floating point number, rather. So I say that x is going to be something like 2.3. Then I can do what type of object is x. Then it's a floating point number. To find out some information about our floating point numbers, we can again import the sys module. And if we do something like sys.floatinfo, then it's going to return an expression that looks like this. So this is going to return some information about how the limits of our floating point number. So here we're seeing float info, the max being something like 10 to the 308th power, the max exponent 1024, probably base 2. Max 10 exponent 308, which is what we see here. Minimum floating point number 10 to the negative 308, more or less. Minimum exponent, again, base 2, negative 1021, 307. Number of digits, we've got 15, mantissa digits, 53. This epsilon now, the epsilon is kind of an interesting number in that this is the minimum distance that we're going to have to be able to distinguish between 1 and the next floating point number. And so to see that that's actually going to be true, let's say that x is going to be 1. And let's say that y is going to be x plus our sys.floatinfo.epsilon. And so now are x and y going to be the same? Well, is x equal to y? No, they are not. But if I would do something like sys.float epsilon float info, dot epsilon, and I do that dividing by 2, then I still get a floating point number, so I get something that's not 0. But in this case, if I do now z equal to x plus our sys.floatinfo.epsilon divided by 2, so now I am taking 1. I'm adding on something that's smaller than this sys.floatinfo.epsilon, and now can Python distinguish between z and x? I know that they are different, but if I ask it the question, they appear to be exactly the same. So are they true as far as Python is concerned? Yes, they are. And so the epsilon there just gives us the minimum separation that we have between distinguishing between one and the next floating point number. And so you can be asking now, well, is that going to hold true for every other floating point number? Can I just add this sys.float epsilon on there and I'm still okay? Is that my how much that I have in here? Well, let's look and see. And we'll see that the answer is going to be no. So let's just even move just a little bit further. So let's take a look at if x was 2.0. Now before, when we represented those values, we could say that, oh, if I just add sys.float epsilon, then it will be distinguished by saying that those two are going to be different. Well, let's add on x plus our sys dot float info dot epsilon. So I know that that's going to be a floating point integer. I know that they're going to should be in the real world different between x. But if I do the test, is y equal to x, now it's true. So our sys.float epsilon is not going to be. Well, you could say, what's going on here? That's kind of weird. Why isn't it the same epsilon for everyone? And the answer is really going to be because when we're storing our floating point numbers, we've got this size of our floating point number before the decimal and our size of our floating point number after the decimal. And we only have a fixed amount of memory space in which to store that. And so the more memory that we need for the front of the decimal, the less memory that we have to distinguish between digits at the end of the decimal. And really those are going to be really kind of determined by of course, our powers of 2. And so if we have, so let's do a little bit of an experiment. So now let's import our math module again. And so if we look at math.log of our sys.float info.epsilon, and we look at that base 2, then we see that it's going to be really something like 2 to the negative 52 power. And so let's see what happens. Let's see if we can distinguish between 2.0 and something around that 2 to the negative 52 power. And so for that, let's do a little bit of a loop. And so let's say that for I in the range from, let's go 50 to, let's go 45. 45 to 55, and I want to print the value for I, and also is x plus 2 to the negative I equal to x. So our x now is 2.0, and so I'm going to print out the power of I, and I'm going to have it print out the comparison between those, and let's see what happens. So if we do that, we can see that for between 1 and the next floating point integer, it is the difference of 2 to the negative 52. But for 2, what power do we have? Well, I can tell the difference. The smallest one that I can tell the difference for is 2 to the negative 51 power. And so because I have more digits before the decimal point, I have fewer digits at the end to be able to tell the difference between those numbers. And so what happens if we increase x by a power of 2 again? Well, now let's make x equal to, we said it was 2, let's make it equal to 4.0. And so if we run that same loop again, let's see what happens. Now we've gone from being able to distinguish at 2 to the negative 51. Now we can only distinguish at 2 to the negative 50. So we've gone from 1, which is 2 to the 0, to 2, up to 4 now, and we can see that we're losing our precision 1 digit at a time. And so because we're dealing with a floating point memory, you gain somewhere, you lose somewhere. We've got a fixed amount of memory that we can store our floating point numbers, and this is what happens. And so floating point numbers are a bit of a different animal. They're an interesting thing to kind of have to deal with. Probably for most of what we're doing, it may not be too much of a concern for us, but it's good to recognize that, oh wow, this is some kind of strange stuff that's actually going on here. So now when we turn ourselves the other direction, so what happens when we start trying to distinguish our floating point numbers from 0? Well, again, coming back to those values, so if we come back and take a look at sys.floatinfo, and we look at those values again, we're seeing that the max is to the 308th, and the min is going to be negative 308. And so if we try to distinguish there, so if we look at is sys.floatinfo.min equal to 0.0, they are not equal. But if I try to do something like, let's say, if I do sys.floatinfo.min, I divide that by 2, they're still not equal. So what's going on there? How low can I actually go before I'm not distinguishing from 0 anymore? And so, again, let's turn to a little loop and see if we can figure that out. And as we're looking at it, we're seeing the minimum exponent here at negative 1021. And so that really gives us a fairly good idea, an indication of maybe what we're talking about here. And so let's take a look. And if I do, well, actually first, before we do that, let's look at math.log of our sys.floatinfo.min. Let's see what that is in base 2. Well, in base 2, that is negative 1022. So the negative 1022 power. We're seeing a minimum exponent here of negative 1021. How much further can we go? Well, let's try. So let's do a little bit of a loop. So let's say for I in X range, maybe let's start at 1022 and let's go up to 1080, and then let's do a check. So we want to print I, and then we want to do a test is 2 raised to the negative I power equal to 0.0. So let's see what this loop will return us. So for all of those values, so for an exponent of 2 to the negative 1022 power, I can tell the difference between 0 all the way down to 2 to the negative 1074 power. Now I can tell the difference, but as soon as I pass that, now I can't tell the difference anymore. And so what's the smallest number that I can distinguish from 0? It'd be about 2 to the negative 1074 power. And so if I actually look at that, 2 to the negative 1074 power, 5 times 10 to the negative 324th power, that's going to be pretty small. So you can ask questions, well, rightly so, what's going on here? You showed me this sys.floatinfo.min value, and it was this. Or if I just look at the sys.floatinfo, again, I'm seeing these exponents of 10 to the negative 324, but I'm seeing the minimum value of max, the min exponent being negative 307. What's going on there? I'm seeing negative 324. What's happening there? Well, again, it's a whole different area of floating point numbers that we could get into. We could talk about normal floating point numbers, and then we could talk about subnormal floating point numbers. And that's kind of an entirely different can of worms that we really don't want to get into at this point. It's not really necessary for us. but generally, as we're just running programs, we're doing our tests, we can still use these values to kind of give us limits to say that, all right, as long as we're kind of using these as our notions of error and we're keeping well within those bounds, our program should run perfectly well and we should be just fine. So a lot of the details we don't really necessarily need to worry about, but it's good to know that floating point numbers are not quite as obvious as what they seem at first blush, and once we get inside a computer, our real numbers are not our real numbers anymore. And so that's probably a pretty good stopping point at this juncture. So let's pick up maybe again in our next video and talking about our sequential data types. Until then, hope you've enjoyed this video. If you like it, click like below. Any questions, comments, anything like that, again, leave those down below too. I'm Dr. Latham, and I will see you guys next time.